Okay, we're on to question 2. A resistor connected with a cell of 9 volts. So we need to draw additional components to measure the voltage across the resistor and the current in the resistor. Okay, and the component that we need to measure the voltage across the resistor is a voltmeter. Okay, now just be careful, those lines have got to touch the circle. Okay, and ideally you want a couple of little blobs to show that they're not crossed wires, they're joined wires, not crossed wires. And then so voltmeter goes in parallel with the component that it's trying to measure the voltage across, and the ammeter can go anywhere in the circuit. Okay, and again, you want the wires going into the middle. Okay, current in the resistor is that much. Calculate the power dissipated. So we need to know the formula that P equals V times I. Okay, I missed a couple of steps there actually. If you want to go back to basics to do it, you can write down what the question tells you, which is that V is 9 volts. It told you that in part A of the question, and that the current, okay, is 0.00191 amps. Okay, and also that we're trying to calculate the power. So that was steps 1 and 2 in the 6 steps of calculation bliss. Now we're on to step 3. There's the formula that links those 3 variables together. Okay, and we've got 9 times by 0.00191. And if you put that in a calculator, steps 5 and 6, here's the answer in the units coming up. You're going to get 0.01719 watts. Okay, but again, we want to look carefully at the level of precision that's been given to us in the question, okay, and give our answer to the same level of precision. So you can see that here that was to 3 significant figures. A bit difficult to know about the voltage. I mean, really, they should have given that as 9.00, shouldn't they? Okay, but if this is given to 3 significant figures, I think giving my answer to 3 significant figures makes sense. So that's 0.0172 watts. What is direct current? It's a current that only goes in one direction. So it's a current that flows in the same direction all the time. Okay, it doesn't change its direction. If it changed its direction, then we would call it alternating current, and an alternating current reverses its current 50 times a second, which is why it's a 50 hertz current. So an example of alternating current is mains electricity. Example of direct current is a battery or a cell. Explain how the current in the circuit changes when an identical resistor is connected in series. Okay, so I'm just going to draw that out just so that we can be absolutely clear about what we're talking about now. So we've got a resistor there with resistance R, and we're talking about putting another resistor in series with it. So some of you had learnt this table brilliantly. Then we've got a series circuit and a parallel circuit like this, and we know the voltage and we know the current, and you'd remembered that in a series circuit the voltage gets shared and the current stays the same, and in a parallel circuit it's the other way around, so it's the same voltage and the current is shared. And you'd looked at this and you'd gone, oh well, it's a series circuit, so the current must be the same. Alright, that misses the point of what this table's all about. Okay, it tells you that the current at this point in the circuit here, I1, is the same as the current here, I2 is the same as the current here, I3 is the same as the current here, I4 is the same as the current here, I5. What it doesn't tell you is what happens if you start putting more or less resistors in the circuit. Okay, So now let's have a think about what's going on. We've doubled the resistance in the circuit. Okay, before the resistance was R, now the resistance is 2R. But we've still got the same 9-volt cell. Okay, so if we have a look at the V equals I times R relationship, okay, this number here has stayed the same. This number here has doubled, times by 2. So what's that going to mean for the current? Okay, hopefully you're good enough at analysing equations to realise that the current must halve if we double the resistance in the circuit. Okay, and that's the end of question 2.